Okay. The thing is that as we discussed the choice of size of V. So we have already seen this estimate, that is a P of X, that we already seen is equal to, that is it is K by N times capital V. Okay, we have already seen it. Okay. Now this is a V is a, so can you see this? Read out the text. Huh?
Yes,
Yes,
sir.
sir.
Okay.
Yes, sir. Yes, sir.
Okay, so we have in the last class that we have seen that is a Px, that is equal to, you would say this is an estimated density, so you can apply some histogram method, that is Ky n times into capital V, where capital V is the volume of around X, in which that if you find that k data points are found of the among the samples within the V, then this will be considered as a good approximate. Now the choice of there is another concept. The choice of size of V is very critical for getting a good estimate. I mean the choice is a choice of size V critical for getting good estimate. Okay, the choice of size V is critical for getting the good estimates. Okay, it means that suppose if your V is sufficiently large, if V is very large, then you will have very I mean smooth estimate. If it is very large, you will have very smooth estimate of this thing. If you are very smooth, then it is not going to have the appropriate estimate. So this is one issue. Another thing is if your V is very small or very small, then that many of the sample points will not fall in the V. So if many of the sample points will not fall in the V, it means that many places the density will be zero. So that's why there is a trade-off between that how we are going to choose the V, and that is a choice of V is critical for getting good estimate. So now that's why there is a two different possibilities that we have already discussed. Possibilities. There is a two different possibilities that we have already discussed. First is that we can fix capital V, okay, and compute A. So this is called this Parzel window or kernel density estimate. Okay. Next one is that you can fix K and compute V. This is called this kernel density. Okay. So now today we'll see only Parzel window. So you need to find one window functions that is called the phi. Okay. So this window function that you need to use. So that is called the phi. That is you can write for simplicity that you define it. That is a define a function. So that is a window function that is phi, where RD, where this is an uh, you have a region Rn. It is a d-dimensional hypercube. Okay, I mean you have defined a function phi, that is window function, where so from the d-dimensional hyper, I mean d-dimensional space to a RD to R, that you need to transform it, and this function is defined in this way. That is that phi u. Okay, so now this phi is a window function, and in the phi you have some data points u. Okay, and this phi u will be 1 if this ui is less than is equal to 0.5. Okay, for all values j is equal to 1 to d, or if it is not, so it means that if the data points are false within this hypercube, then it is 1. Okay, and if the data point does not fall within the hypercube, and because if it is range, so actually it is a unit hypercube, so that's it is 1, because a unit hypercube means this is a length is 1. So I mean this is a size, or length of each side is 1. So that is, it is called the unit hypercube. Okay, and UI is less than is equal to 0.5 and or 0 otherwise. Okay, where you could have that you have u is equal to u1 till u2 till u3, okay, till un, that you could find. Okay, so it means that, yeah, you need to define a function in such a way, so this function is called the window function, that is phi, and the points are belonging to, if the points are belonging to the hypercube, then and if it is a range of, actually it means that ui is less than is equal to half, means this total range, it is a -5 to minus 0.5 to plus 0.5. okay, now it is 1, it means if all the sides are 1, I mean this is an I mean unit hypercube means this side of, or the length of each edge is, that is a 1. So that is why it is this this function will give it to this value is phi of is equal to 1. Or if it means that if the data points are belonging or fall, if the data points fall within the hypercube, then it is 1. If the data point does not fall within the hypercube, then it is 0. So this function, it is denoted by this phi u, where let phi u can be a window function. Okay, or you can say that this is a kernel functions. It may be considered as a window function. Is something is known as the kernel functions. So now this kernel, this is a kernel function, and this Vn, capital Vn, it is equal to hnd, where hn is the length of the edge of Rn. Okay, so now the concept is that we'll see this way that this defines a unit. Actually, this defines a unit hypercube in Rd. In you'll have in d-dimensional Euclidean space. Okay, centered at origin. Okay, centered at origin. Now point U is inside unit hypercube. Point U is inside the unit hypercube in Rd. I mean, if okay, if point, you can say if point U is inside the unit hypercube in Rd, because as it is a d-dimensional space, then that's why you can have this is hypercube steps. Okay, in Rd. Okay, point is inside the hypercube in Rd, then okay, the function will be 1. Okay, then the window function, then the window function, that is phi, is 1. Otherwise, it is, and note that is phi u is also symmetric. Okay, where I could get phi. Okay, so phi u is equal to phi of minus u. It is also a symmetric function. So these are the main things that this defines the function, that is a phi u is equal to 1 if uy, I mean if all the points or all the points in the range of the d-dimensional space, okay, that is in the range of if it is less than or equal to 0.5, I mean it has a length from minus 0.5 to plus 0.5. Total length is 1. Okay, if phi is equal to 1, if it is in the range of phi u, I mean absolute value, so we are taking the absolute value, so that is why it is 0.5. Okay, if you take consider this entire space, okay, and then you will have this is a minus 0.5 to plus 0.5, and these are the functions. So this function is very important. Now what you could do, you have to define, so this is a window function. So actually this function non-parametric method can be useful in the base classifier. So in the base classifier you have to compute this is a density function px. So now your job that is to px. Okay, you have to use it, this function you need to use it in your base classifier. So that is your main job. So now before that, I am just going to tell you that is you have a phi. I'm just going to write some mathematical things that you need to understand. That is there's a phi. Then you have u minus u naught minus u naught by h. Okay, hypercube of side h and centered hypercube of side h centered at u naught. Centered at u naught. Okay. Now let d is a point. I mean d is a d is a data samples. Now let d is equal to data samples. That is you have x1 comma you have xn. Okay. You have now you have a data points or you have with the data samples. Okay, then for any x, then this function can be written, that is a phi of, we need to write phi of क्या होगा x minus xi divided by h would be 1 only if this xi only if this xi falls in a hypercube. Okay, falls in a hypercube of side h centered at x. Okay. So now the concept is that, so what is the meaning of x minus xi by h? So x minus xi, this is a translation. That's it. And h is called the scaling. So whenever you have some function, current function, in the current functions, so you need to have some transformations from one point to another point. So this ऊपर वाला part जो है, So it is x minus xi. So it is called the translation, and I mean the numerator is called the translations, and the denominator you will have the some scaling. Okay, and because these are the points. So as you can see in the here it is written this function, this phi of x minus xi slash hn. Okay, so now the hn means in number of data points, or if it is an if you are considering for capital D, so it means hnd means that is a d is equal to x1 to xn. You have that many data samples. Now the phi of x minus xi by hn is equal to unity if xi falls within the hypercube of volume Vn centered at x and equals to, okay, and if it does not fall in this volume V, okay, then it is 0. If xi does not fall in the V, then it is 0. Now as I already told you, there is a how to choose the size of volume. The size of volume is very critical. If you choose a very small size, then this xi, many of the xi will not fall into the volume. If many of the xi will not fall into the volume, it means the density is 0. Okay, so that is the concept that you need to understand. And the number of samples. Now, if you just want to consider, if we apply the histogram method, that the number of sample in the hypercube. Okay, now if you could write in this way, the number of, so hence the number of data points falling in the hypercube of site H centered at X is as follows. Okay, क्या है ये वाला k is equal to, or if you have this k is equal to, I mean that is, so if you just remember the formula, what was the formula from the histogram means that is a f dash f at x is equal to k by n times capital V. यही तो था. Okay, now this side that you can have this k is equal to 1 to n. This is a phi of x minus xi into h. So now that many points. So the number of points, number of k points that can be computed by using this formula, summation of I is equal to 1 to n phi of x minus xi divided by hn. That is the concept. Now if you just substituting k in this equation, if you could obtain so these things. Okay, Pn is equal to, now the hypercube of side H in RD has volume. I'm just going to write it here, some comments, so that it will be more clear to you. Okay, now this hypercube of side H, hypercube of side H in RD in RD into d-dimensional real space has volume H to HT. That is HT. Okay. So now the hypercube of side H in RD has volume in HD. So hence we can have our estimated density function okay as follows. What is it? This. Okay, so now by substituting this k in the equation 7, we could obtain. So these are the equations. So if you just follow it in the previous equation, that is a this equation. Okay, you have 1 by n, I is equal to 1 to n, 1 by Vn, or you can simply write 1 by h to the power d phi of x minus xi by hn. So this density is called the mixture density function. Why it is called the mixture density function? Because for every values, okay, because xi is equal to I is equal to 1 to d, for each dimension, so you will have the different density function. So now that's why it is called this, and it is also known as the Parsons window estimate. So this estimate Pnx is equal to 1 by n, I is equal to 1 to n, 1 by Vn, or you can simply have 1 by Vn. So what are the formula? क्या था उसका? K by nv. So these are the formula. K by n into v. So k is that phi of x minus xi by hn. Okay, v is vn, and you can simply have, that is the k. You just simply have the estimated is equal to Pn is equal to k by n into v. So these are the formula that we have already seen. You just plug in it and you would get this thing. Okay, 1 by hd phi into x minus xh. Okay, so this estimate is called, that is a density estimate. Is that clear? Have you remember the formula for the Pnx is equal to Kn by n divided by Vn? If you follow the last class, you just substitute the value of Kn in the equation. Kn by n, if you have this, either numerator will be Kn by n, denominator will be Vn, or you can simply have Kn by n, I mean small n times Vn. So small n times it is 1 by n, it is just bringing back, then I is equal to 1 to n, 1 by Vn. So 1 by Vn can be written by 1 by h to the power, I mean d, because as the hypercube of side h in Rd has a volume h to the power d. So it is known as this, this function is known as this, your Parsons density window, or you can say the kernel density function. You can simply have this function. It is a density function. This is an estimated density function. This is called the estimated density function, and based on these 5 functions that you will have to choose. Okay, this kernel may be a Gaussian kernel. This kernel may be a radial basis kernel. This kernel may be a trapezoidal kernel. It depends. This kernel may be a like this polynomial kernel. So there are a lot of kernel functions are there. Okay, you have to choose this kernel in such a way so that you could just estimate this density. Okay, so now it means that, so these are the main thing formula. We are simply using this histogram method. Okay, that is, and you are just plugging this Kn, means how many number of points fall in the V. So if that many points are fall in the V, then this kernel function is 1. If it is not, that is 0. So that is the main concept. Now Pnx, estimate Px, it is just, now this is an estimated value, or in books also, in some other books also, it is written fx and f at x. If it is fx means actual, the fx is estimated. Now Pnx means this is an estimated, because on the based on this the number of samples on the data in the d-dimensional space. And Pnx estimate the Px, which is an average of function of x, because you have a average of function, you have a lot of functions are there. For one function, two function, I mean in functions are there. Okay, because as you have the hn. Okay, because there's a some scaling is there hn for each functions that you are just going to averaging it, and this is called the mixture density function. Sometimes if you have the mixture of all the functions, all the kernel function, then it is known as mixture density function. Okay, so it is an average of function of x, and the samples, as I told you, xi is equal to I is equal to 1 to n. This function phi can be of any form. So as I already told, it may be a Gaussian, it may be some other functions, so on and so forth. So now what we can conclude like that, if we store all xi, I will take xi from here. If we store all xi, we can compute, okay, pnx. We can compute pnx. Okay, at x. It is an estimated density. pnx at x. Okay, and the value of h determines size of volume. Okay, now the value of h will determine the size of the volume. Then you will have pnx is equal to 1 by n is equal to 1 to n 1 by h to the power d, or you can have v to the power n. That is where this v to the power n is equal to h to the power d. That is known already. So now this is a kind of generalization. This is a kind of generalization of the histogram idea. Okay. So we are simply reacting reacting beams where needed and counting. Okay, we are just simply applying the histogram formula, that is a kn by n by v, or kn by n times capital V. Okay, so these are the things that we are doing. So now this function has got few properties. So this function, the properties of phi. So can anyone tell me what are the properties of phi? Can anyone remember what are the properties of density when a function is called a density function? What are the two properties that it will satisfy, because it is a density function that I am claiming?
The integration of from infinity to infinity is 1.
Okay, another is it must be positive.
Yes.
Greater than 0.
So now the function, should satisfy phi u is greater than is equal to 0, and integration we have integration rd then you have phi u u is equal to 1. Okay. So now the hypercube window. Now the hypercube window function which we use satisfy, let's say DIA. What are this? Now what will be your V? So you'll have only V is equal to phi mu by h u is equal to RD phi u minus u naught is du. Okay. So this hypercube window functions which we use. It's satisfied. I mean, this is a volume. So I'm just telling you. I was just telling you this is a volume that it needs to be computed. This is RD phi u by h, or you can simply have u minus h, or you can for our hypercube window. So for our hypercube window, V is equal to HD, that you know already. V is equal to, you know already, h to the power b. Then the estimate will be Pnx, the same thing, that is in you have Pn Pnx is equal to, that is 1 by n. Okay, summation of is equal to 1 to n 1 by v 1 by v. Then you have 5 x minus xi x minus xi by h would be density. Okay, ठीक है. So this now if if Pnx, if it satisfies, if Pnx would satisfy property. Okay, it will satisfy, that is in Pnx is greater than or equal to 0 for all x, and integration of Pnx ds is equal to 1. Okay. Now we can choose many phi function that satisfy this earlier condition. We can choose many phi function. As I already explained, many phi function. That is a Gaussian. Actually, phi means it is in kernel functions. Okay, you can choose. So you can choose many phi functions that satisfy the earlier conditions. What are the conditions? Integration of, I mean, the function phi u greater than or equal to 0. This function must be positive. Okay, and the area under the curve is 1. Okay, then with appropriate v, we get a density estimate. Okay, so this method called kernel density estimate. Okay. So now we'll see for the Gaussian case. We'll see for the Gaussian case, as I already said. So this function, as I already telling you, so before going to the Gaussian function, so this function must satisfy some condition. The condition is that is fx is greater than or equal to 0, or pnx is greater than or equal to 0, and integration pnx ds is equal to 1. So now this function, yes, yeah. So now the behavior of the Parisian window. So case where if you the px, if you have this n is a, it is a normal. Okay, mean 0 and the variance is 1. Okay, now let if you have as I already explained, so these are the function 1 by hn phi of x minus xi into h. It is an average of normal density centered at sample xi. So now phi u is equal to 1 by root over 2 pi 1 by root over 2 pi to the power d. So if you simply have in this way, phi u is equal to 1 by root over 2 pi to the power d x here minus half. Okay, or minus u square by 2. You can simply have in this way, and hn is equal to h1 by that is a square root of n, where n is greater than 1. Okay, so in this way also you just plug in, or then simply you can have. So the formula you can also rewrite in this way. That is a if you consider a d dimension Gaussian density, then phi u, you can design phi of u, you can have that is 1 by square root of 2 pi 1 by square root of that is pi 1 by root over 2 pi to the power d. Okay, then you have exp xp of minus half minus 1 by 2, then you have Euclidean norm, Paradic norm, there's a mu square. We can also find this formula. Okay, it is a single dimension Gaussian. Okay, that you can have, or you can have the single variant for this phi. So you can have for this phi, capital V is equal to this. Okay. So now, if the density, now this density now we estimated. How you are going to estimate the density? That I'm just keeping. So now this is a summing all the contribution content with respect to PDF. So now actually the dotted line is called, this is an mixture density. Now this is an actual density which will cover this all that density. Now summing the contribution of the content. So these are the mixture density. If you, I mean individual density. Now if you just sum them up, so if you have the mixture density. So now if you just summing the contribution of the all the coordinates to obtain a partial PDF estimate. So this one is the partial PDF estimate. So now if you just put some result, that is you put n is equal to 1, h1 is equal to 1. Then if you have p1, then you have p2, then p3 for each things. Okay. Now x minus x1 is equal to 1 over 2 pi to the power minus half into x minus x1 squared for x1 comma 1. Now n is equal to 10, h is equal to 0.9. The contribution of the individual samples are clearly observable. So you can take as an assignment that you just plot it. Okay, you just put the value and you just put the density function. That's it. So actually in your lab also you can find some the programs that put the values and you can see the density function, what are the nature of the density, then you can plot it. So it is just like that. Okay. It is just the dimensions, different functions that is there. Now it is actually there, it is there from this book, like this Dudar book. Now if you take these things as a classification problems, now how you can apply it in a base classifier. Now how do you design a classifier based on the partial Miller density function? You take a Gaussian kernel. Now if you take the Gaussian kernel, now I'm just writing over here. If you take that is in now this density will be estimate. Now the density estimate now is you will have if you have this Gaussian taking the Gaussian case at each data point and representing this unknown density, then how you are going to represent it. That is we'll have taking this thing. Now take this in P and X series. So P and X is equal to 1 by n, then summation of I is equal to 1 to n. Okay. that is 1 by h square root of 2 pi square root of 2 into 2 pi. This one will be d. Okay, exp and exp of minus. We are just simply applying the formula for the Gaussian. Minus half. Okay, and instead of here we are going to take, so you can take square of x minus xi by 2 h square. Square. This is for the Gaussian, because whatever function that you are going to choose for your coordinate density, it must be satisfied with the two conditions. Okay, that you need to be sure. Now we are essentially we are essentially taking the Gaussian centered at taking some Gaussian GAUSSIN Gaussian centered at each data point and representing the unknown density as mixture of this Gaussian. Mixture of this Gaussian. So now if you have this Gaussian, आपको मिल गया Gaussian, then you'll have to do a compute this mu and sigma. Okay, that that you have to means compute. Now you have to again means apply it these functions with this mu will be mu and sigma, that has to be used. You apply the Emily method, maximum likelihood method. Okay, to compute it for the mean and variance, you have to again compute it. So for this mean and variance, you have to take this expected value of mean, and you have to take the expected value of variances. Then you can finally get this answer. Okay. So now you can follow the book. This is a Dudard book. I'm taking from the Dudard book. In chapter number 4, page number, you can see this 164. You can follow that whatever things that I am explaining to you, so it is already there. Okay, and only the I just wanted to. I'm not telling. I'm not going to get into details of these things. Okay, I'm just leaving it at your end. Okay, so it is the derivation is there into the book. Okay, if you understood the concept Emily method, so now then by applying the Emily method, you can simply use it for computing this mean and computing the variance, because we have already seen that one Emily method, that what this variance is given unknown variance, unknown mu, that you have how to compute it, that we have seen, and if you the variance is given an unknown mu, how do you compute it, that you already see. You can simply apply this formula and you can estimate these functions. Okay, so this is just a mathematical way of representing it, and finally when you are going to use it for your classification purposes, this needs to be understood. How do you design a classifier based on the Parsons window? So Poisson window density function means if the density function is not given to you, and if you do not have any functional approximations, then you need to apply these one functions, okay, and which is closer to the histogram, means that is a k by n times capital V. So now that's the way you can I mean think of it, and you can design your own approximations. Then you have to estimate the class conditional density for each class. As we have already seen this river and non-river class, that the assignment that I already given to you, and there is a multivariate question was given to you, but you have to here estimate the class conditional density. There is a PNX that needs to be computed. How do you compute it? The process that I already explained. So and then estimate the class conditional estimate for each class, and classify a test sample by the level which is corresponding to the maximum a posterior density. That is we have already seen. Okay, this is for the maximum a posteriori density. That I mean, actually it is just a posterior density that whenever I was explaining to you this maximum likelihood estimate, so I was already telling that the two things was given. If the posterior density is given, you can directly compute the posterior density, okay, and that then computing the posterior density is P of capital P Wi by given x. This is a posterior density. Then you have to compute for each class that which maximum a posterior density. So after taking this class conditional density for each class, both the classes you compute this posterior density, and which one is the give it to the maximum value, then that would be the maximum posterior density. And the decision region for Poisson window classifier depends upon the choice of window function. That is the very important decision region, because you need to classify it, and you have some decision boundary, and in the decision region where the two classes, if you take the binary classes, will have the good distinctions. So now decision region for a Poisson window classifier depends upon the choice of the window function and the window width. Okay, that is we are using, this is an H is there. Okay, window width, and in practice the window function that we are going to choose this Gaussian. Okay, so this is the things that you need to maintain. One is called the to understand the Poisson window, that how do you choose this. As I already told you, so there is a to choose the volume V. If you take the volume is very large, obviously you don't have very good estimate. If volume is very small, then also I mean the maximum data points that you are going to choose, that is K, will not fall into this volume V. So now that's why you need to find a window width. So window width, that is to be I mean choose in such a way so that this maximum data points fall within the region, small region, that is called the V. Okay, then obviously you can get a very good estimate. So this is called this Poisson window, and the decision boundary, it is there from the Dudart book also, and some example is there in this book. So now today I'm just stopping here. So here we have seen only one possibility. Okay, now the choice of size of V is very critical of getting a good estimate. So that is why we are using these two possibilities. One is that we can fix the V, okay, and you can compute this number of data points. That as you can see, we have computed this number of data points, that is in Kn. So Kn that we have already computed means how many points are actually falling into the V. Then this is called the Poisson window. Tomorrow I'll take one extra class because I want to complete this portion, and from Monday onwards I'll start a new chapter that is called the regression analysis. So that's why tomorrow I just wanted to take one class for completing the nearest neighbor density estimation. Okay, so probably in the second half I'll take. First half, so I'll be busy. So second half, so from 2:15, is it okay?
Excuse me, sir.
Yes.
We have a lab from 2:15.
So tomorrow is Saturday, no?
Sir, but yes, sir. But the lab on the Wednesday was shifted to Saturday.
Every Wednesday's lab on Saturday.
No, sir. Only this week.
215 to 315. So you are in which branch?
So software engineering.
Software engineering. Who will be taking your lab?
So Professor Rat, sir.
In the morning, huh?
Sir, in the morning from 11, DP sir will take the extra class. Before that, we are free.
And IS and other section? Computer science?
Sir, for IS, we have no scheduled class for tomorrow.
Yeah, you don't have any schedule, huh? Good, very good. So you have a lab from 215 to 515?
Yes, sir. Full flash lab, sir.
Huh? 3 hours?
Yes, sir. Yes, sir.
Okay, from then I'll take from 5:15 to 6:15. Is it okay? Because I'll take only half an hour or 45 minutes class. Only just wanted to complete this.
Yes, sir.
Destination. That's it. Okay, so I'll take from 5:50 to 6:50. Okay.
Yes, sir.
Or you want me to take in morning?
So morning would be better.
So morning, sir.
Yes, sir.
Morning better.
Okay, morning सबके लिए better होगा ना? Okay.
Yes,
morning.
sir.
Okay, morning is better na? So 8 to 9 is okay.
Yes, sir.
Yes, sir. Yes, sir.
Because I just wanted to complete it by the early morning so that I think I should take from 8 to 9. Okay, so tomorrow at from 8 to 9. So I'll start at probably on 8:15 or 8:10. Okay, so today it is not a scheduled class. So it is just an extra class because to compensate one of my mothers, I missed 2 classes. So out of 2 classes, I already compensate 1 class, and 1 class is left. Okay, so that's why I just wanted to compensate it. So probably I'll start at 8:05 or 8:10. Okay, you can join. So I'll take only half an hour or 45 minutes to complete this k-nearest neighbor density estimation, and also tomorrow we'll give it to you some solve problems on this topic. Okay, so I know it is a little bit of mathematics, so you need to understand it. Okay, and until or unless you implement it, so we'll also give it to you this implementation step also, and how to do this Farjan window, and as well as for this Maxwell-Lively estimation and the density estimation. So last class assignment have you submitted to Joyita? Any one of you has got the correct output that I have shown in PPT? Or is it still pending?
Sir, in case of river and non-river class.
Yes. So the assignment, no, that.
Yes, sir. I didn't get the exact one, but my accuracy was above 80%.
80%. And the picture, I mean the images.
Yes,
there
sir.
Have you shown with images?
Yes, sir. Can I share my screen?
Okay, I'll learn because I have because there is some PhD interview is going on, so I need to join it.
Okay, sir.
So I'll see afterwards. Yes, super.
Hello, sir.
Yes.
Sir, do we need to show it as an image, the output as an image, or we can take just the screenshot?
What screenshot?
When we plot it using what was that? Sir, using Matplotlib, when we plot it, so do we have to share just the screenshot, or we have to save it as an image?
You have to save it as an image, JPEG image. Okay.
Okay, sir.
Some Subra Sarkar. So do you have any question?
Sir, I got the result as an image, sir.
Good, good, very good. So the exact images that I just shown through my PPT.
Yes, sir, not that exact, but
So you need to find the accuracy. Yeah? So accuracy is important. Okay.
oh, okay, sir.
Okay. Okay.
Okay,
Okay.
sir.
So tomorrow I'll see because in the tomorrow's lab I'll just sit with you because and I'll just check. And next week and also you'll get very good assignment on I mean on this face biometric system that you need to develop. Obviously steps will be given to you in the next assignment. Yes.
Actually, sir, good morning. I am a student of this executive PhD batch. So the assignments are in the lab section. So do I need to do that also?
No, I think for executive PhD student you don't have any
We have
compulsory.
only the theory.
Yes, you have only theory class, so there is no compulsory, and you will not get any credit for this email lab. I think. But if
Okay,
you
sir.
want to join, so you can join. No, I mean no issue. As it is an online class, so I don't have any problem. Okay.
Okay, sir.
Good morning, sir.
Yes.
Hello. Sir, I'm in PhD. I'm also not assigned the class, lab class. So I was seeing the assignment. I had a problem. If though there were some small water bodies on the southwest part of the map, southeast part of the map, sir. During the can we just classify it along with the rivers, or we need some other parameters to differentiate between the river and those water bodies?
No, means water bodies that we are not considering. Okay, because obviously it is on satellite images. Satellite images, if you have the different region of these things. Okay, so our objective was to how you have to take some points from the river region and you have to take some point from the non-river region. So I could specify it by 50 and 100. So you could have taken more sample or less samples. So it's up to you only. Okay, so means as it is a 2 class, but whenever you could also differentiate with the 3 class. Okay, suppose you want to classify it, if you could just spot these 3 different places in this region. Okay, suppose whenever this assignment you will have to implement it in K-means clustering, because when I'll be teaching you the K-means clustering, so same satellite images you'll have to take, and for you will have to divide it into K different clusters. Okay, now the K different cluster means more pixel values will be cluttered where there is there is a similarity of the distance is there between the pixels. So that many pixels will be cluttered in one place. Okay, are you understanding me? So now that you are telling there is some water region portion is there in the non-river part also. Now,
yes, sir.
Yes, I understood. So now if you now apply the K-means clustering algorithm, now if I choose K is equal to 6, 5 or K is equal to 7, now you'll see that because this river region part which is there in the non-river part, so it will be automatically clustered as the sample points are very near
closer to the river point.
Yes, around the mean. So it will be automatically clustered out. So actually I have kept it for the clustering problem itself.
Okay, sir. Okay.
So you could also see whenever we just get to know the clustering problem. So it will automatically cluster.
Sir, if somebody takes it mistakenly in the non-river